Relativity. If a ball is thrown from one stationary person to another at 3 meters per second, it will arrive at 3 meters per second, ignoring gravity and air resistance, of course. Here we have the person throwing stationary and the person catching on a skateboard approaching at 2 meters per second. If the catcher is on a skateboard approaching the thrower at 2 meters per second, the relative velocity of the ball to the catcher will be 5 meters per second. When Einstein formulated his special theory of relativity, it was based on two postulates or statements. These were that the laws of physics should be the same regardless of the position or motion of the observer, and also that the speed of light in a vacuum is constant. What these statements mean is that if, instead of a ball, the people were passing light, both should find the light has the same speed. So here are our two stationary people again, and the person on the left shines light towards the person on the right. The person on the left, if they were able to measure the speed of light leaving them, would find it was going at 3 times 10 to the 8 meters per second, and the person on the right would find it approaches at 3 times 10 to the 8 meters per second. No great problem there. However, consider this situation. Now we have two people in spaceships travelling towards each other, both with a speed of 2 times 10 to the 8 meters per second. The spaceship on the left shines light towards the spaceship on the right. Now what Einstein said was that the person on the left would see the light going away from them at 3 times 10 to the 8 meters per second, and also the person on the right would see the light approaching them at 3 times 10 to the 8 meters per second. The velocity of approach of the two spaceships has no effect on their measurement of the speed of light. This situation has some very strange consequences, as I'm about to show you. Imagine we have a clock that consists of two mirrors, with the time being measured by light passing up and down between the mirrors. This is represented by the yellow ball going up and down in the diagram. Here we have one of these clocks on a train. Two observers watch the clock. One is on the moving train with the clock, the other is on the platform. According to the first postulate of Einstein, the laws of physics should be the same for both observers. Also, according to the second postulate, the speed of light should be the same for both. As the train passes, the man with the clock will see the light go straight up and down, maybe 4 complete times, a distance of 8 times the separation L of the mirrors. The man on the platform, however, will see something like this. Here are the mirrors, a distance L apart, but as the train moves along, the man will see the light leave this mirror, hit the top mirror, then down to this mirror, and so on. Now, this length here is greater than L. So the man on the platform sees the light travel further at the same speed, which must take longer. If he had his own light clock on the platform next to him, the moving clock would be going slow compared to his stationary clock. We could consider the argument from the viewpoint of the passenger, and he would see the platform clock, the one that is moving relative to him, running slow. So we see from this argument that moving clocks go slow. This effect is actually observed in nature, but it only becomes apparent if the speed is close to that of light. One example is that of muons. Muons can be created in the laboratory and are found to have a lifetime of about 2 microseconds. Muons are also created in the upper atmosphere by cosmic rays. These muons are travelling at around about 98% the speed of light, and they're found to have a much longer life when measured with clocks stationary relative to the Earth. It can be shown that this equation is true, where t is the time measured by a clock moving relative to the object being measured. T0 is a clock that is stationary relative to the object being measured, so it could be a clock travelling with a moving object. V here is the relative speed between the two clocks, and c the speed of light in a vacuum. Let's see how this equation applies to the fast-moving muons. So there we had a time of 2 microseconds according to the muons themselves, but we were observing them at a speed of 98% the speed of light. So to work out the speed first, the speed will be 98% of 3 times 10 to the 8 meters per second, the speed of light. This comes out at 2.94 times 10 to the 8 meters per second. Now, putting the numbers into this equation, we get that the time will be 2 microseconds for t0 over the square root of 1 minus the speed of the muons squared over the speed of light in a vacuum squared. This gives a time of 1.0 times 10 to the minus 5 seconds, which is about 5 times as long as 2 microseconds. Another strange effect, which is actually observed in nature, is that as objects travel faster, their mass increases. Mass increase is given by this expression, where m is the mass of the moving object, m0, what is called the rest mass, the mass of the stationary object, over this same expression, the square root of 1 minus v squared over c squared. Let's find the mass increase of a Typhoon fighter aircraft if it's travelling at a speed of 680 meters per second, with a rest mass of 20,000 kilograms. I've put the numbers here into the equation, but 680 meters per second is so small compared to the speed of light, 3 times 10 to the 8 meters per second, that we end up with this, 20,000 kilograms over 1 minus 5.1 times 10 to the minus 12. Now this will not register on your calculator, it comes out as just 1. And so effectively we have a mass of 20,000 kilograms. Even at this speed, twice the speed of sound, the change is far too small to register on your calculator. This shows us that we can ignore relativistic effects in all but the most extreme of cases. The Large Hadron Collider does achieve speeds very close to the speed of light, so they need to consider relativistic effects. The extra energy it gives to the protons appears as a mass increase, not a speed increase. If the protons reach the speed of light, you can see from this expression that this would be c squared over c squared. Anything divided by itself is 1, meaning this bottom section would be 1 minus 1, or 0. The square root of 0 would be 0, and anything divided by 0 is infinity. So the protons would have infinite mass. They would require an infinite force to get them to infinite mass, and so this is clearly not possible. And another consequence of Einstein's laws is that anything with mass cannot travel at the speed of light. Another effect at speeds close to the speed of light is length contraction. It can be shown that for moving objects, their length is equal to their rest length multiplied by the square root of 1 minus v squared over c squared. So the faster an object moves, the shorter it becomes. This effect, again, only becomes apparent at speeds very close to the speed of light. In most calculations, relativistic effects can be ignored.